Brian? Brian? You went to the first slide. Did you? Okay. Yeah, all right. Didn't know if you meant to. Hello. Hi, everybody. My name's Steve Kirchhoff. I'm the chair of the math department here at Stanford, and I'd like to welcome you to tonight's lecture by Professor Brian Conrad, who's a professor here at Stanford in the math department. Tonight's lecture is one of a series of public lectures that is organized by the math department and is sponsored by the Stanford Math Research Center and the Friends of Stanford Mathematics. Before we start, I'd like to tell you a few things about Brian. He grew up in Long Island and got his undergraduate degree from Harvard, and then in 1996 received his PhD from Princeton under the guidance of Andrew Wiles. He spent a few years as a postdoc back at Harvard and at the Institute for Advanced Study at Princeton, and then moved to the University of Michigan in Ann Arbor as an assistant professor. He quickly moved up through the ranks there in Michigan, and then in 2008 we were very fortunate to attract him to Stanford, where he's been since as full professor of mathematics. Brian is well known, won a career award from the National Science Foundation and is a recipient of a Sloan Fellowship. He's well known for his research in number theory, particularly his role in completing the solution to the modularity conjecture. His research includes analyzing problems involving symmetry, which is the topic for tonight's lecture. But I think the thing that strikes everyone who meets and gets to know Brian is his sort of amazing enthusiasm for and his breadth of knowledge in mathematics, and also his pretty amazing level of energy, which seems to be out there at 24/7. But beyond his research accomplishment, Brian is a very popular teacher and is extremely involved in our undergraduate curriculum. He also has been instrumental in the creation of and support of our undergraduate colloquium that meets every week. So we're really delighted to have Brian here to speak to us and to share his thoughts about Rubik, Escher, and Banks. Please join me in welcoming Brian Conrad to the stage.
Okay. So thank you very much for coming. So I want to begin with a quote from Hermann Weyl from a book he wrote called, appropriately enough, Symmetry. And so in this quote, he's sort of commenting about how ordinarily we first encounter symmetry when thinking about the structure of leaves or other things we see in nature, or maybe certain buildings or mountains that we look at. But that in fact, aside from its aesthetic aspects, within the theory of symmetry, there's a beautiful mathematical substructure that's lying down there, which most people don't know about, but which in fact helps us to understand many things that we would think are interesting even if we didn't know about that mathematical theory. And so in tonight's talk, I would like to try to convey some sense of that to you. So we'll first look at some examples of symmetry that come up in various settings, and then we're going to focus on three core examples to illustrate how sort of thinking mathematically about symmetry gives us some nice insight into things. There's much more I would like to say than I have time to say, so I apologize in advance if some of my discussions seem a little bit abbreviated. So after discussing Rubik's Cube in some respects, we're going to talk about some artwork by Escher, in particular these two pictures. The one on the left is called Circle Limit 1, and that's a picture, it's meant to be thought of as some black birds and white birds. You can see their eyeballs. And they're arranged in some way in a disk, and you can see a kind of 120-degree rotational symmetry if you spin it around. But there's clearly something interesting happening at the boundary, and one might want to understand what is the real nature of that pattern. And then there's this other work of Escher called Print Gallery, in which we start with some guy standing in an art gallery on the left, and he's looking at a painting, and then as we kind of go around and look at the buildings in the painting on the right, and then we go around and there's this veranda, and underneath that is an art gallery, which is the same one containing the guy we started with. So it kind of wraps around and comes back to itself. And Escher was apparently got massive headaches thinking about the construction of this, and he was kind of confused as to what goes in the middle, and so he just put his signature in there. And so we'll discuss how it was eventually solved to figure out what actually belongs in the whole. And then the third example we'll discuss is the problem of secure communications over the internet, in particular when you use your smart card or where you set up a bank account without ever contacting in person anybody in the bank. But we believe that it's really a secure connection. And how is this possible without ever having prior contact? And so these three topics look like they have nothing to do with each other. But in fact, we'll see that from the viewpoint of symmetry, thought of mathematically, in fact, there are close connections. And in particular, the mathematics that underlies this picture on the right is, in fact, crucial in this application to smart cards down below. Okay, so we're going to begin with perhaps one of the most famous examples of symmetry in the world, which is in the city of Agra in India. And so it's the Taj Mahal. You have to ignore these people on the bottom because they ruin the symmetry. But in any event, so when I took this picture, I was standing somewhat far back. And we'll see later as we go through the talk other pictures that are much closer, and the symmetry is much more intricate than just this kind of two-sided symmetry. But in this particular case, we can sort of say that the two-sided symmetry is realized by the idea that if you took a large mirror and you sort of passed it vertically down the center, then the part of the Taj Mahal on the right side, the image in the mirror, would in fact be exactly what's on the left side. So there's this kind of symmetry in the sense of reflection through a mirror. But for other purposes later, I'd like to describe that idea of reflection without any mention of mirrors at all, purely in terms of the notion of distance. So let's think about reflections in a slightly different way. So let's imagine we have a line here, and I'm going to have a point off the line, and I want to think about how to describe reflecting the point to the other side of the line. Now, first of all, notice that even the notion of line can be thought of purely in terms of the notion of distance. It's often said the shortest distance between 2 points is a straight line, and indeed, straight lines are precisely those paths with the property that for any 2 points on the path, the part of the path between them is as short as possible. Okay, so that's the line. We have the point off the line, and then on the line, there's exactly 1 point closest to P among all other points on the line. And now we have 2 points, and we draw another line through those. And now if we go from the red dot to the black dot, a certain distance, and then keep going that distance to the other side, then we get to the reflection. Okay? So in that way, we've described the notion of reflection purely in terms of our notion of distance. And you should just keep this in the back of your mind because we will pull this out of the fridge later in the talk. Okay? So that's this notion of reflection, this two-sided symmetry. But if you go to the back of the Taj Mahal, there's a much more interesting kind of symmetry. And so this is, well, it's not literally the ground because, well, there's some dirt and stuff over on the right. But anyway, so this is some tiles that we have here. And there's some dark regions and some white regions. And they create some kind of interesting pattern. But the perspective in the camera makes things get smaller. So we'll just make an idealized version here. Right? So it's really the same thing, right, if you look. And so imagine this pattern continuing to the right and the left and the top and the bottom. And so we see that each dark region is surrounded by 4 white diamonds. And if you think about them together, they form an octagon. And each octagon has 4 neighbors around it, but they do overlap in these little white diamonds. Okay? And if we think about this a little bit, we can draw 4 kinds of lines through the center of the dark region. We have a horizontal line, vertical line, and 2 kinds of diagonals. And these are lines of symmetry in the sense that if I reflect the picture across any of these lines, I get back what I started with. Or in other words, the whole picture looks the same if you imagine reflecting it through a mirror to the other side. Okay? And on the other hand, another way you can think about this is the octagon has 8 corners, and they come in 4 opposite pairs. And these lines are just joining the opposite corners. All right? And said that way, you might think, wait, this thing also has 8 sides, and so why don't I also make lines joining the midpoints of opposite sides? But if you do that, then it sort of ruins the symmetry because it doesn't cut the dark region in a sort of exactly through the middle. It kind of sort of screws up. So these are not lines of symmetry due to the dark figures inside. So we have these 4 different symmetric directions through the center, and of course we could choose the center in many different places. So this is a highly symmetric situation. Also, we can spin the whole thing 90 degrees and keep spinning it. And indeed, if you look back at the picture, you'll see, right, if you rotate it 90 degrees, you get back what you started with. And if you do that 3 times, that's the same as rotating 90 degrees in the other direction. Okay, so we have this nice rotational symmetry. And there's also some translational symmetry. If you imagine starting on the left and sort of shifting over 1 octagon unit to the right, you again will get back what you started with. But the interesting thing is that this translational symmetry is in fact a consequence of having enough reflectional symmetry. And this is most easily seen in this picture that I stole off the internet. So there's a girl sitting in a room, and maybe you've had this phenomenon if you have in your house, you have a room with mirrors on opposite walls. And so she's in a room looking at a mirror, and behind her is another mirror. And the interesting thing is, if you look at the mirror within the mirror, okay, sort of 2 stages in, so that's 2 reflections, and then you see there's another copy of the same girl translated forward twice as far as the distance between the mirrors. Now, you might think this is completely fake because that's just an artificial image in a mirror, but in fact, if you go back to this picture, if you draw 2 parallel lines of symmetry and you reflect through one and then reflect through the other, in fact, you'll see that the whole image translates twice as far in one direction. So this translational symmetry is in fact a consequence of having enough reflections. Okay, so let's just summarize what we've discussed about these ideas of symmetry. So we start with some object built from pieces. So it might be the tiling behind the Taj Mahal, or this arrangement of blackbirds and whitebirds, which somehow seem to get smaller as we go out towards the boundary circle, or this Rubik's cube built up from these little tiny cubes. And so when we speak about symmetry of such a situation, roughly what we want to imagine is that we rearrange all the parts in such a way that it preserves some properties that we specify. Okay? So it might be distance. For example, in the Taj Mahal, in the situation at the back of the Taj Mahal, these reflections and rotations, if you started with 2 regions at some distance, after you reflected or rotated, they again were at the same distance. Now with the Rubik's Cube, of course, distance is not such a good notion because when you twist one face, the pieces start moving away from each other. On the other hand, the colors are kind of carried along in a good way. So you have to sort of choose in any given situation what properties you want to be preserved under the rearrangement. And the 2 things to keep in mind is anytime you have 2 symmetries of a situation, if you apply one and then the other, you might get a new one. Okay, like we saw that in the case, the back of the Taj Mahal, just from having enough reflections, if we composed 2 different reflections like that girl in the mirror, we got translations as a bonus. Okay? And at the same time, any symmetry that you apply, you can always undo it. Okay? Now, of course, in the case of the Rubik's Cube, that might be easier said than done. But anyway, one other thing to keep in mind is that when we're thinking about composing different symmetries with each other, the order can make a huge difference. So in real life, this is a familiar situation. If you think about entering a room or opening the door, that makes a difference in whether you break your nose. On the other hand, in the case of Rubik's Cube, this is a familiar phenomenon that if you ever try to follow one of those books which purports to tell you how to solve it, and then if you get the order of 2 maneuvers out of sequence, then of course everything gets all screwed up. So it's very important to pay attention to the order in which you compose symmetries with each other. But there are situations that will come up later where in fact the order in which you apply things does not matter. And curiously enough, the situations that are relevant to the symmetries hiding inside your smart card, in fact, use very much symmetries in which the order of composition does not matter, and that insensitivity is in fact quite crucial to why the security of these systems actually works. Okay, so now let's turn to the first example that we want to discuss, which is Rubik's Cube. So there on the right, we have Mr. Rubik. This is a picture of him from a long time ago. And needless to say, this puzzle gave him a much better salary than he was getting as an architecture professor in communist Europe, so he became a very wealthy man. And when we speak about the symmetries of the Rubik's Cube, what we mean are the motions you get by applying successive legal maneuvers. Okay, so you can rotate a face. What you're not supposed to do is my preferred method, which is you jam a screwdriver in there and you pop the pieces out and then you reassemble it. Okay, so that's not a good move. Okay, so the symmetries refer to compositions of legal maneuvers. Okay, and before we discuss those symmetries, I want to point out a situation which one might call false advertising, which is when you buy a Rubik's Cube in the store, they often the packaging tries to impress upon you how hard this puzzle is. And so they say it has many moves, has 43 quintillion, that's 18 zeros. So it's a trillion trillions, right? So this makes the national debt look like pocket change. And so this is many, many positions. There's the exact number that I've written up here. And here I've written it as a somewhat more complicated looking fraction. So this 8 with the exclamation point, we call this 8 factorial, which is 8 times 7 times 6 all the way down. 12 factorial, 3 to the 8, 2 to the 12th, divided by 12. Now the reason I wrote it this way is, first of all, when one counts this number of positions, you don't, of course, write down all the positions of a Rubik's Cube. There are ways of counting without counting, so to speak. But this formula is sort of interesting because, in fact, this numerator, I won't have time to discuss it, but in a certain sense, this is relatively easy to explain using screwdrivers. But this 12 is much more subtle, and that has something to do with rather non-obvious properties of the symmetries of the cube that, unfortunately, I do not have time to discuss. But anyway, the reason I'm mentioning all this is that, surprisingly enough, the reason that the Rubik's Cube is hard is not because of what it says in the package. It's not because the number of positions is so large. Now, of course, you're not going to believe me if I tell you that, so I'm going to show you an example which will convince you that this is not really the reason it's so difficult. And so we're going to look at another puzzle that you will never find sold in any store that's not going out of business. We call this the alphabet puzzle. Okay, so what's the alphabet puzzle? It's a really stupid game. So you arrange the letters of the alphabet in some order along a line. And the puzzle, but don't laugh, is you just have to put everything in alphabetical order by swapping 2 letters at a time. Okay, now this is a very easy puzzle. It's a very silly game because all you do is, well, we'll put A in the correct spot, so we just swap it with whatever in the first spot. Great. Now B is somewhere in here, so you look for it, you find it, and you swap it with X. Fine. C is over here at the end. So you swap that. Well, it should go in the third spot, but remember, that's actually H now. So you swap C with H. Anyway, you keep going, and after 25 moves, it's over, right? A through Y are in the correct spot, and Z has only one place left to be, so you're done. Not a very difficult puzzle. Okay. But the number of positions turns out to be 26 factorial, which is about 4 followed by 26 zeros, which is 10 million times more positions than the Rubik's Cube. Okay? So, needless to say, just the size somehow is not really the reason. There's some subtle thing relating to geometry and algebra, which I don't have time to get into. So now let's turn to the cube itself. So here on the right is a cube that I disassembled using my screwdriver. And you see the inner workings there, this brilliant system he has. And one thing, the reason I did this was, aside from the fact that this is my favorite method of solving it, is notice that here we have orange on the top and orange on the top, yellow on the right, blue on the left. Here's the other way around. No matter how you rotate this, you will never get this configuration. Different cubes have different color schemes. So when we talk about motions of the cube, using the colors is a bad idea because it's not good from one cube to the next. So we're going to describe things instead in terms of some geometry. And so we're going to think about what we're going to call the 6 basic moves. So we have the positions up, down, right, left, back, and front. And for each of these, you imagine facing head-on. So imagine you were over here looking at this right face. And then the basic move R will be 90 degrees clockwise. And similarly in these other directions. Okay? So for each of the 6 directions of facing it head-on, we have what we'll call a basic move. And that's just 90 degrees clockwise. And if you do this 3 times, you will get 90 degrees counterclockwise. Okay? So if you use these basic moves, you will get all the motions of the outer faces. All right? But that's not everything, right? Because you might say, wait, but what if I want to take this middle slice here and rotate that maybe 90 degrees towards us? But you see, Instead, you can just take the parallel outer faces and rotate them 90 degrees away, and then up to just moving the whole cube in space, that has the same effect. Okay? So in fact, you can achieve all standard motions of the cube, in principle, just by using these motions of the outer faces, provided we ignore rotations in space. And certainly, you wouldn't regard rotating the cube in space as giving you any progress anyway. In any event, but the thing to observe about these basic moves is that the center square it might spin, but it doesn't change its basic position. So using the basic moves has the nice advantage that the centers always stay in a fixed spot. Okay? You wouldn't necessarily use this in practice, but it makes it easier to discuss what's going on. Okay. Now, the main difficulty when you try to solve this thing is, of course, that maybe you get the bottom face. That's good. And maybe if you're clever, you get the second layer. Anyway, at some point, depending upon your skill level, you usually reach the place where you run into this psychological obstruction, which is you have to start destroying things that you've already achieved. And at least for me, my failed attempts to do this when I was a kid, this was a big problem, because you don't really want to give up what you worked so hard to achieve. Anyway, and so what I would like to explain to you is, so let's imagine we're in this situation on the left, where this has this guy, and this guy. This is almost solved, 3 things out of place, and it's pretty clear if you're ever going to solve this, you're going to have to start messing up some other stuff. Okay? And so what I want to do is describe to you a maneuver that achieves this, but the point of telling this to you is not that you're going to memorize it, because that's completely, I can't memorize anything, but there's going to be something very interesting about the nature of the maneuver, which is in fact a general feature of all solutions, all systematic solutions to the cube. And rather than going from the left position to the right position, which is what you would want to do, just for ease of explanation, visualization, I'm going to tell you about going from the right to the left, because it's easier to start from the solved position and go to the left. But of course, you could then just reverse everything and do the more interesting direction. So I'm going to describe to you 2 basic maneuvers from which we're going to achieve this going from right to left. So X is going to denote the following composite maneuver. So we start here, all right, with some position, but we'll describe it using geometrically. You take this so-called right face, and you spin it 90 degrees counterclockwise, okay? So the orange goes up like this. I'm sorry, clockwise, sorry, okay. 90 degrees like this, and then we're going to take the top face, and we're going to spin it around this way, which is whichever it is, counterclockwise, okay? And then we go back to the right face, and we undo what we did before. We bring it back down, right? So this is orange, red, red, orange, red, red. Okay? So this is just this 3-step process. It's gotten kind of messed up, I agree. Okay? But notice one thing, which will be relevant in a moment. Along the bottom, the only position in the end that got messed up was this one down here, or this closest right corner. Okay? So this composite maneuver we'll call X. And then just one more Y, very simple. We just take the bottom and we just give it a spin 90 degrees counterclockwise if you're facing it from below. Okay, the blue gets shifted around here. That's called Y. Okay, and notice this only affects the bottom. All right, so X and Y, in terms of the physical positions they affect, the only position they affect in common is the only piece on the bottom that X touches, which is this piece down here in the end. Okay, now if you apply this to X, you get that mess. Okay. So you apply X, you get Y, you get this horrific-looking mess. All right? But the thing I want to emphasize about these 2 maneuvers is that the physical positions that they both affect, there's only one in common. That's the important point. Okay, and now what we do, having done X and then Y, we then undo X and undo Y. All right? If you undo X and Y, and then and then you get this final position, which is what we wanted to achieve. Now, that was all very complicated looking, and it seems like a miracle that all that mess somehow got almost wiped out in the end. But in fact, there's a completely general mathematical theorem about rearrangements that has nothing to do with Rubik's Cube, which explains this phenomenon and certain general phenomenon one finds in all systematic solutions, which is any time you have a finite set of objects, like the pieces of a Rubik's Cube, and you have 2 rearrangements, X and Y, whatever they may be, with the feature that there's only one position that they both affect, then if you apply X and Y, and then do the opposite of X and the opposite of Y, the end result is always going to be a rearrangement of only 3 pieces. Which pieces they are, you can describe in some way that I won't get into. But the point is this apparent miracle where everything almost canceled out is in fact just some general fact about the mathematics of rearrangements. It has nothing to do with Rubik's Cube. And in fact, if you look in a book of systematic solutions to Rubik's Cube, you will find these kinds of operations over and over again. Not necessarily with this particular x and y, but there's always this feature that for some appropriate x and y, it's always do x, and then y, undo x, undo y, and then you get something nice. Okay, and the interior mess cancels out. And so thinking about symmetries in a kind of broader mathematical context reveals this kind of general feature, and in fact, this is what you find in all of these solutions. So in fact, thinking about symmetries in a sort of broader setting does help to illuminate certain general features of these sort of systematic solutions. I'm not going to tell you anything more about solving Rubik's Cube, so now we move on to Escher. But one thing, again, keep in mind this business with the order of composition. So here's a picture of Escher. So he was an artist in the Netherlands, and he had no formal training in math, but he, of course, had tremendous insight into geometric structure. And he had made many examples of these sort of planar tilings, where you take kind of weird, not like triangles and squares, right? You have three people, like this kind of in white, this slightly shaded person, and this darker person, and they're interlinked in some complicated way that repeats itself in the plane. So this is unbounded in all directions. But then he kind of seized on this idea of infinite repetition in a bounded region. And he thought this, he somehow had this idea this should be possible, but he ran into some problems implementing it. But there was a great classical geometer, Donald Coxeter, with whom he was in contact, and they discussed this. And then one day, Coxeter sent him this picture. Okay? And so the thing I want you to notice about this circle is we have this rather complicated arrangement of green pads here. These are actually pieces of other circular arcs, and they have the property that they meet at 90 degrees on the boundary. But it's not obvious what this arrangement of arcs is. They're getting smaller and smaller, but it's kind of complicated. In any event, this picture, which we will discuss in some detail, this in fact inspired that arrangement with the black and white birds. And we'll see a little bit later what the link is between the two. But Escher faced a practical problem, which is if you're going to make this as a woodcut, you need to know how to actually construct all these, well, at least down to the, some small level. You have to make a lot of these little circular paths. The question is, how do you do that? Okay? And so Escher was quite mystified, but he made some progress. Okay? So he had the following observation. Here's the thing we would ideally like to construct. This is Coxeter's picture. So Escher realized that if he drew a square on the inside and then made a circle of the same size as the original through two consecutive intersection points, and then he got the center, and then he spun that around by 60 degrees, that in fact these circular arcs would be exactly the biggest ones. So that was nice. And then he thought some more, and he realized that if you connected these centers, and then you get this hexagon, and then you make circles whose diameters are the sides of that hexagon, then you got the next smaller circles. That was nice. And then he thought a little bit more, and he was like, hey, okay, now it gets complicated. So if you take each of these diameters and you cut them in 3 parts and you make 2 circles per diameter, okay, you get the next. Then it gets really complicated. And let's not get into what he was doing there, but the point is then he got stuck. Okay? So he kept coming up with new and more clever ideas, but at some point he kind of got stuck, and he asked Coxeter, like, what's going on? So this is not systematic. This is a matter of being clever, but maybe Coxeter would have some uniform answer. And with his brilliant brevity, he just did this. He just drew a little circle and a line and sent it back to Escher. So not very helpful. In fact, Escher told his son, it's like, yeah, those pure mathematicians, very, very helpful. Okay? I'm omitting some more nasty things that he said about Coxeter later in the quote. Okay. In any event, so what I would like to explain to you is not what Escher eventually came up with, because we don't really know, but mathematically, what's really going on in that picture. In particular, it looks very asymmetric. You have the big arcs and the smaller arcs, and they get ever smaller, but it turns out there's an amazingly rich symmetry in this picture, which is very hard to see at first sight, because it turns out you have to use non-Euclidean geometry. But to explain what's going on, we're going to go back to India, and we're going to take a look at this window on the side of the Taj Mahal. And so here's a close-up. This is a very familiar hexagonal pattern. And these hexagons, they have 2 basic lines of symmetry, which are the ones joining opposite sides in blue and the ones joining the midpoints of opposite sides in red. Okay? And I want to focus, in fact, on the ones joining opposite sides in blue. So if you think about a reflection through this line joining these opposite sides, if you keep the line going, you see then it goes through an edge. So rather than thinking about lines that join opposite corners, you can instead think about lines that go through an edge, and what you're doing is you're reflecting through edges. Okay? And so this basic pattern of hexagons can be obtained starting with one hexagon, and then you start reflecting it through all of its edges, and reflect those, and reflect those. And so you keep reflecting through edges over and over again from one hexagon, you'll get the entire array in the kind of unbounded plane. Okay? So this is a way of getting the entire picture. And I claim that this visualization with the hexagons going off in all directions, in fact, is what's going on in the Escher bounded picture with the ever-shrinking things towards the boundary. So to understand, so here's, you see, they are kind of related. Okay? And so in here you have the big, funny hexagon with the kind of curved sides. And notice that you have the big, large birds in here. And then you have slightly smaller ones here, which are shrunken exactly according to the length they need to fit exactly on that piece. In any event, so once you have this arrangement of birds on the big hexagon, the question is, how do you figure out what's happening around the boundary? Okay, similarly here, once you have these big arcs, what do you do to get the other ones? So Escher made a little progress, and then he got stuck. Okay? And so let's imagine that we could make the large ones, and I want some systematic way to produce all of the smaller ones. So how do you get all the rest? It looks very asymmetric in the sense that this hexagon in the middle is much bigger than everything else. Notice, however, that if you go along this side, you have 1, 2, 3, 4, 5, 6. So this weird region in here is also a hexagon, which looks nothing like this one, but I claim that from a certain point of view, it is the same hexagon. And so I want to explain what's going on there, and to do that, we have to make a little detour through what I'll call curved geometry. So it's a kind of familiar fact from school that if you try to make a map of the Earth on a flat piece of paper, that there's inevitably some kind of distortion. Okay? And this is, of course, the general theorem in math, that there's just no way of achieving this that doesn't distort at least one of distances or angles or something more. So here are two kinds of maps. This one you don't usually see. This is a very familiar one called the Mercator projection. And this preserves angles. This faithfully reflects angles on the surface of the Earth, which is very useful when you're doing navigation. Okay? But it distorts area, right? So, like, for example, Greenland looks like it's the same size as Africa. Antarctica looks really gigantic. But in fact, Africa is 14 times larger than Greenland. Okay? So this is not very good for getting a sense of area. This so-called Lambert projection, it distorts angles. Well, you can sort of see that. But in fact, it preserves ratios of areas. Okay? So this is a map on a disk, but this has good properties for angles. Okay. And, well, here's another aspect of what we might call spherical geometry. So on a sphere, if I give you 2 points, and you want to find the path on the sphere that's shortest length between them, well, you basically draw an equator that passes through those points, so-called great circle. Okay? But as you know, if you've ever flown in a plane, like going from San Francisco to Bombay, that the path you take, which is in fact a great circle on the Earth, when you look on this Mercator map, looks kind of weird. Okay? And if you go to Perth, right, it seems you take a funny bend in the middle. But in fact, this is just the distorted effect of a great circle under the Mercator projection. And so the point is, paths on the sphere that look very clean and pretty and that minimize length, when you put them on a flat surface, they look very different. Okay? Well, it turns out there's another kind of surface called a hyperboloid, not a sphere. And on that surface, there's also a notion of minimal length paths, analogous to these equators. And there's an analog of the Lambert projection, which puts hyperbolic geometry on a flat piece of paper, in fact, on a disk. Okay? And we call that the Poincaré disk. And it turns out that when you take the length minimizing paths of the hyperboloid, what you might call the lines of hyperbolic geometry, since in usual geometry, lines are the length minimizing paths, then in fact you get exactly the arcs in that disk. Okay? So from a certain non-Euclidean geometric perspective, those arcs are in fact length minimizing paths. And that's great, because we saw at the beginning that if you have a line and a point off it, you can reflect across a line just using your notion of distance. So in this geometric world, these are the lines, and there's a funny notion of hyperbolic distance, and if you reflect this through this so-called line, you in fact get this region. So in fact, this whole thing is just a matter of reflecting hexagons through hyperbolic lines. It's in fact a hyperbolic analog of exactly that window at the Taj Mahal, except it takes place in a region that looks bounded to us from the viewpoint of Euclidean geometry. Okay? So that's the rule mathematically that describes what's happening in this picture, but only by taking the viewpoint of non-Euclidean geometry can you see the massive symmetry in here that you see more transparently when you look at that window at the Taj Mahal. Okay, now here's a practical application. So 2 weeks ago, this is just amazing timing. So 2 weeks ago in Foxtrot, which I don't ordinarily read, but Google does, so I found it. So here was the cartoon, okay? So dad is making pancakes for breakfast in different shapes, okay? And then his genius son comes along, and, well, okay, he wants the 7-gon tiling of the Poincare disk using hyperbolic geometry. And she has the advantage that you can make as many pancakes as you want on the disk of the pan, right? So it's great, okay? Except there's some problems with pouring the batter, but anyway. Okay, so that's hyperbolic geometry. Now, so there, the symmetries are quite non-obvious until you change your perspective. Now, in this circle, in this so-called print gallery, this other Escher picture, there's this spiral phenomenon that we noticed. But it turns out the geometry underlying this is rather different. The symmetries in here are rather different from those lurking inside the circle limit picture. And in the year 2000, the mathematician Hendrik Lenstra was on a flight between the US and Europe, and he was looking in a magazine, and he noticed this picture, and he wondered to himself, he saw the spiral symmetry, and he wondered, is there a way of filling in that hole that's more satisfactory than writing Escher's name? Well, here's an interesting quote from the book Gödel, Escher, Bach. So Douglas Hofstadter says, no, it's impossible. Somehow that would violate, inconsistent with the rules. And, the center, can't get rid of it. Must be incomplete. In fact, that's not true. So Lenstra, in fact, realized that by using certain ideas of John Tate from 1959, he was, in fact, able to fill in the hole. And I'm going to explain to you what it was. So here is well, maybe not in this particular example, but this is a kind of familiar situation. You have a picture within a picture within a picture within a picture within a picture. And Lenstra realized this is some kind of warped version of this. Of course, you don't have Homer and Bart sitting in here somewhere. But it should be some kind of analog of this, where this picture created by Tate is somehow guiding what's happening here. And more specifically, Lenstra realized that by using certain things called elliptic curves, which are not ellipses, I'll explain what they are later, they're lurking inside your smart cards, he was able to, in fact, fill in the hole. So here's the picture, and in fact, by working with a couple of colleagues, they were able to fill in the hole. So I'll do this a couple times, then we'll see a movie. So you have to keep in mind, Escher did everything just by trial and error, because he didn't know anything about elliptic curves. So it's actually kind of amazing that he got pretty close to getting it on the nose. And so the whole thing is, what's happening in there? Okay, so let's see that. So let me just pull up this movie. Window. Oh, where did it? Enter full screen. There we go. Okay. All right, now ready? Watch. Okay, so this is gonna loop. So we're gonna spiral in, and you'll notice in a few seconds something fun, but we'll loop it several times because it's gonna give you a headache. And so as we get, you see, there's the guy again. Okay, don't worry, it's gonna jump at a certain point because just from the film. But anyway, yeah. So there he is, and now we'll just do this a couple times. You just try to see if you can guess where's that guy. Okay, I don't see him yet. Where is he? Where is he? There he is. Okay, there he is. Oh, okay. All right, so let's, we'll do it one more time, okay? There's a website, you can just sit there all afternoon watching this, but they also, you can put other pictures, and anyway, so let's do this one more time because that was so much fun, and there he is again. Okay, that was very nice. Okay, so anyway, yeah. Okay. But I did not make that movie. Okay, so anyway, all right, so that's the story with this picture. So I haven't told you, I should say, 10 years ago, Lenstra came here and gave an entire public lecture just on that, okay? So I'm not going to tell you anything more about it. I will tell you what elliptic curves are for some other purpose, but this is not the time or place to get into the math that lies in there. So now we're going to move on to internet banking, okay? Now, there's a fundamental problem. You see, in World War II, right, when the Germans, and they were exchanging all these secret codes every month, and you had people running all over the place to give the submarines next month's logbooks, right, with all the encryption keys. And, when you sit there and you buy something from Amazon, I mean, you haven't had a communication with them, but you trust, and it does work, that people are not tapping into your credit card numbers. And it's a kind of remarkable thing that internet commerce relies on the property that you're trying to communicate with somebody else. And even if somebody is tapping into the line through the entire conversation, you're somehow able to set up a secure link so somebody who's listening the whole time can't tap in. And if you think about it, this seems completely impossible. I mean, how can you do that? Okay? So in 1976, these three gentlemen, so Whitfield Diffie, Martin Hellman, who's at Stanford, and his graduate student at the time, Ralph Merkle, who contributed important ideas to this, they figured out how to do this by using a certain kind of symmetry in number theory. And they did this in 1976. They called public key cryptography. And the following year, these three gentlemen at MIT, Ron Rivest, Adi Shamir... Sorry. Sorry. Okay. I had a choice. I should say, somebody told me I should do color picture of them more recently, but I thought it was nicer to do the one from then. Okay. And then Adelman, so it's called RSA. And then the mid-'80s, these two gentlemen, Victor Miller and Neil Koblitz, came up with a much more efficient way of implementing their ideas using geometry, what's called elliptic curve cryptography. And this is, in fact, what's used nowadays in smart cards. It only requires 1/10 the number of digits in the codes. So before I explain to you what elliptic curves are and how they're used, I want to first convey a kind of slightly fake but illustrative example of what the basic idea is in public key cryptography. And so we're going to this example, though, I'll explain a certain fundamental defect, but the defect will be overcome by using elliptic curves. So let's pretend that you have some secret number. You haven't told it to me, so we'll call that your private key. But you do reveal to everybody 2 to that number. So, for example, maybe it's this beast here. Now, if you happen to know about logarithms, you know that if you tell me 2 to the a, then I can figure out what a is. If you know about logarithms, just pretend for the sake of the moment that you don't know. And if you don't know about logarithms, that's even better. So the point is that let's pretend that given this number here, it does not compromise a. So a is still private, even though everybody knows this. Okay. Meanwhile, I have my own secret number, but for the purpose of this discussion, I'm going to tell you it's 48, but pretend you didn't know that. But what I will reveal to the whole world is 2 to that number. Okay, that's my so-called public key. All right, and it's this beast over here. All right, now here's the amazing thing. So each of us knows our private key, A and B. Nobody else knows them, but everybody knows the public key. And if you know your private key and somebody else's public key, you can do something that can only be done by the other person who has the other private key. And what is that thing? It's just the law of exponents. You see, if you want to compute 2 to the AB, it's either 2 to the A to the B or 2 to the B to the A. So if you know my public key I know your public key and I have my private key. You know my public key and you have your private key. And from this, you can compute this common number. But if you don't know any of this, you can't do anything. Okay? So this common number is something that we can both compute using our private number and your public thing that you told everybody, and nobody else can compute this. Okay? Well, here it is. Okay? So I have your public key was this, my private number was that, and that's the number. Okay? Nobody else is going to guess that at random. It's a pretty good secret. Okay? And the point is, unfortunately, some people know about logarithms, and so the problem with this method is, in fact, revealing 2 to the a compromises the secrecy of a. So that's not any good. Okay? But now I'm going to tell you about elliptic curves, and this is going to bypass this problem. Okay, so what's an elliptic curve? So an elliptic curve, well, here's a picture of one here. Okay? So it's the solutions to an equation of this form where s and t are some numbers, like s could be 0 and t could be 8. So we'll just work with this one. Okay? And we see this has some nice symmetry when you reflect it across the horizontal axis. That's just because the equation is invariant under this maneuver. But it turns out that there are many, many, many other symmetries respecting a certain algebraic structure on this curve, which are very difficult to see at first sight. And the fundamental difference is every earlier example of a symmetry, like a rotation or a reflection, in fact was an operation on the entire ambient space. Okay? And then you restricted it to your particular situation. The symmetries on this elliptic curve that I will show you can only be understood in terms of the curve itself. They have no interpretation in terms of the ambient space, and this is why these are very difficult to perceive, but it's also part of the secret to the magic of how they're useful. So let me illustrate to you an example of a symmetry of this curve. So for every point, I'm going to create a symmetry. I will just illustrate it in this picture with this point. So here's what you do. I give you any blue point at all, and then you draw the line, connecting it to your red point. Miracle number one, but this is a quirk of these cubic curves, it always cuts the curve in one more point, the black point. Then you take the black point and you flip it across the x-axis, across the horizontal axis, and you call that point built from these P star Q. It's just notation. Okay? And so fixing the red dot, associating to every blue dot a corresponding purple dot, which is some kind of weird rearrangement of the points on the curve, this is our symmetry depending on P. Okay? And notice that if you change the roles of the red and blue dots, the line doesn't change. So, in fact, this operation is insensitive to order, okay? Just like addition, like the insensitive to the symmetry order. This is the real miracle, which I don't have time to explain at all, that the so-called parentheses don't matter, although if I hadn't mentioned it, you probably wouldn't have worried about it. But mathematically, this is the real miracle that underlies what we're going to do with this. But if the 2 points happen to be the same, you see if the blue dot gets closer and closer to the red dot, then this line joining them becomes more and more like the tangent line. So let's see that. So if you draw the tangent line, in some sense it has a double order contact here. And so the tangent cuts it again at one more point, and you reflect and you get a green dot. All right, well here it is. Oh wait, we can play the same game again. Let's now connect the green dot to the red dot, get a new black dot, reflect that, and get a cyan dot. Okay, now you can connect the red dot to the cyan dot, you get a new dot. Well, unfortunately it's way off the screen down here, and you flip it back up to the top, and it's that. Okay, and you keep going. All right, and you keep doing this over and over and over again. And so this iterated symmetry of P star, many times, okay? This is something that really can be done on a computer. The denominators get pretty nasty, so you don't want to do it by hand. And so this is going to be the key to everything. Now, how is this relevant to smart cards? Okay? Well, the first thing I have to tell you, we observe that this star operation is like addition. The order doesn't matter and the parentheses don't matter. So I'll just, for notation, if I do P star P, I'll call that 2P. And in general, if I do this some number of times, I'll just write AP to save the typography. And so this has two properties that are very useful. First of all, if you star P against itself A times, and then star this thing against itself B times, that turns out to be P starred against itself B A times. It's like multiplication of numbers, except this P is not a number, it's a point. Okay? But notationally it looks nice. But much more serious is this. There is no analog, practical analog of division. If I give you P, and I give you an iterated multiple of P, there is no known practical method that will reconstruct the multiplier. Okay? Unlike logarithms, given 2 to the A and 2, you can reconstruct A. Here, there is no analog. Okay? Why is that useful? Okay. Well, every smart card, believe it or not, has inside of it an elliptic curve and a point. Okay? In fact, there are about 15 elliptic curves. If you go into Google and you type in NIST elliptic curves, National Institutes of Standard and Technology elliptic curves, some of these might even be patented. These are particularly robust for these applications. So you just have one of these with a point, and this is told to the entire world. Okay? And this is the analog of 2. All right? Everybody knows 2. All right. Now we go through the same game. The bank has a secret number. Your smart card has a secret number, and these are unknown to everybody. You keep them off the grid, and you might change them later, but they're secret. Okay. Now, the analog of exponentiation, take the known point on the known curve and hit it with your secret number, and you tell that to the entire world. Okay? That's the public key. Everybody knows B times P. Everybody knows P, but because there's no elliptic division, so to speak, only the bank knows its original B. This does not compromise the privacy. All right, now you do something mathematically very simple. Okay? Well, the smart card has its private number. It knows the bank's public key. And it just stars that against A that many times, and it gets this number. Notice I did not know B. I just knew this, and that was enough. Similarly, the bank has its private number, and it knows the smart card's public key, so it does the similar maneuver. But BA equals AB, right? Because multiplication of numbers is commutative. And so therefore, you see, the bank and the smart card both have the same information, and nobody else knows this. This is a secret, okay? And since there's no analog of logarithms, this is really a secret. And the point is, in some sense, the real mystery, of course, I'm not telling you how you set up a fast system or anything, but just in principle, this is a proof of concept. It's possible to securely exchange some secret information. Previously, it was this gigantic 30-digit number, or whatever, but that collapsed because of logarithms. And in this case, it's this point on this elliptic curve. But once you have that secret, you can use that to set up a more secure password system and then have a regular communication. Okay? And so that's the real magic of elliptic curves. And in fact, there are many, many other parts of math where ideas in symmetry show up. Fourier analysis and geometry and representation theory and so on. And these were invented at all kinds of different times. And you'll notice that the practical applications often came late. Look, 1801 to 1976. Now, it's always hard to predict what's going to be useful. So this area of math is called group theory. Well, okay, this guy had a slightly incorrect prediction because group theory turns out to be crucial for the classification of fundamental particles and many other things, and Voyager spacecraft. Anyway, so it's very useful for many, many things. But it's a kind of whole big world out there, and I'm happy if anybody's interested, I can give you these various web pages, and there are certain books that explain these things in more detail, and there's an online website where you can play with Rubik's Cube if you don't have one at home, and so on. And so there's a whole big subject, and there are many, many beautiful applications, but the math itself is also intrinsically quite pretty, and one important thing to keep in mind is that often the mathematicians, they study these things purely for sort of mathematical reasons, and we have no idea what's going to be useful. But again, if you just look at this list, when Riemann in the 1850s, right, was studying high-dimensional geometry, he was never imagining that, for cars to get around, they're going to have to use the relativistic, time transformation in the equations. Give me a break, right? So it's very hard to predict what's going to be useful, and so we don't know what parts of math will be useful in the future, but that'll be a subject for some future talk. Okay, I'll stop there.
Thank you, Brian, for a wonderful talk. Brian has offered to answer some questions if people have them. We have some microphones over on the aisles here. If you think if you have a question you'd like to ask and are anywhere near the edge, it might be quicker to go over there. We can try from the middle also, but you'll have to yell. So why don't we start with you then?
Hi. So that was terrific. Thanks.
You're welcome.
So I was curious to know if the dimensionality, if you start to increase the number of dimensions, you've shown sort of things on a two-dimensional plane, or most of your examples. Does it still hold up as you go into an additional...
Does what still hold? So the whole theory of symmetry works in whatever arbitrarily many dimensions means. It works in arbitrarily many dimensions, and it's certainly the case that for real-world problems that depend upon many unknown parameters, it's extremely useful to, even if the underlying problem is some concrete thing with airplanes going through this many airports and whatever, but you can still describe these problems in a geometrical language that looks like higher dimensions, and so that is very useful.
So like in the Rubik's Cube, if you have 4
by 4, yeah, sure. I don't. Again, my skill with the Rubik's Cube is pretty bad. So, but yeah, in principle, you could certainly imagine maybe even putting on the computer program with coordinates higher dimensional Rubik's Cubes and thinking about the groups involved. But I don't know anything about that.
Okay, and then just one other thing.
Yes.
How does a group like the NSA break into something like the elliptical curve encryption? I'm just kind of curious if it is truly as secure as you suggest.
So first of all, I should say two things. So I'm a pure mathematician, so I know the math that's involved. I should say, first of all, I have no idea how how do you put the elliptic curve onto the smart card. I don't know anything about engineering. So I also don't know anything about the efficiencies that are involved in, how do you crack systems. So unfortunately, I don't know any practical information. Sorry.
Did you have a question?
Hi.
Yes.
So Rubik's Cubes have been a hobby of mine for a long time, but I never really understood a lot of the math behind it. So this was really interesting to me. So one thing I've noticed there are a couple of things phenomenal that I've noticed about the Rubik's Cube. I don't know why they happen. One of them is that if you take a screwdriver to the cube and you put it back together, except you've changed a couple of things.
Okay. Then you can't resolve it.
Yeah, well, I mean, there are some times you can. If the only thing you've changed is you've taken 3 corners and you rotated it, then it's still solvable.
So in fact, remember when I wrote the number of positions of the cube as this big number, and then I wrote it as some numerator divided by 12. Okay?
Right.
So hiding in that 12 is the answer to your question. But more precisely, what's really going on, so strictly speaking, if you take the Rubik's Cube, you unassemble it with a screwdriver, and you randomly put it back together, there's only a 1 in 12 chance that you can actually solve it. The point is, loosely speaking, that given any screwdriver arrangement of the cube, there are certain computations you can make. And these computations are invariant under legal moves. All right, under legal moves, and if you, but it's possible that the output of these computations for the solved position is different from that of other positions, and so if they're different, then you can't actually get back. The point is, I can tell you more afterwards. I won't get into it in this audience, but it's very much related to. Have you ever? So there's this thing called the 15 puzzle, right? Where you have 15 things in an empty box and you move them around, and you can't flip 2.
Yeah.
Okay, and so the math that explains that is the same. So I can tell you about that afterwards, but it involves the notion of signs and permutations.
All right, thank you.
Yeah.
Beyond the scope of this textbook.
Kind of. Yeah. Yes. Any other?
Are there other questions from anywhere in the audience?
Yeah.
So your art gallery that was expanding.
Yes.
It never seemed to get to the middle.
Right. So no. So strictly speaking, what's happening in the art gallery picture is you take out the center point. Okay. You're supposed to really visualize this plane as the plane of complex numbers. And when you take out the 0, these are the non-zero complex numbers, and they have nice behavior under multiplication. And there's nothing that goes in the center. But it would be very a simple analog would be if I looked at the positive part of the real line, and you picked some point, you started halving it and halving it and halving it and halving it, and you always stay positive and you never get to 0. And in a certain sense, that's a sort of analog of that. So you're right, there's nothing to put in the middle, but you can fill in everything else. Yeah. Yeah.
Really great talk, by the way.
Yeah.
I was just wondering.
Can you just talk into the microphone? Sorry.
So I was just wondering, one of the problems with Diffie-Hellman key exchange is that it's vulnerable to quantum computation.
Okay, so the question is that so I should say I know nothing about quantum computers. Again, I don't know anything practical. So apparently, if quantum computers are ever developed with enough strength that they will crack this Diffie-Hellman system. And so the basic problem is that quantum computers can rapidly factor. Okay, so that's one. Now, I don't know why that is. I don't know anything about quantum computers. So, yeah, I'm not sure what else to say. But this is if you can develop faster computers that do things exponentially quickly, then you can overcome some of these time lag problems. But I don't know anything about how that would be implemented, so you'd have to speak to somebody who actually knows about quantum computers.
Well, I was just asking in terms of non-deterministic computation, how that applies to elliptic curves and why elliptic curves aren't vulnerable to this.
I'm sorry. So I should say the elliptic curve system is resistant to certain kinds of attacks on the Diffie-Hellman system. So the Diffie-Hellman system is vulnerable to something called index calculus, and I can tell you later, but there are certain features that the Diffie-Hellman system has that make it vulnerable in certain ways the elliptic curve is not. But I can't explain that in front of the audience, but I can tell you afterwards.
In the middle there? Can you?
Yeah.
That's you. Can you stand up when you ask a question?
The key exchange algorithm processor inside these smart cards is generally something very cheap and relatively slow commodity. I'm surprised that you do that much math in a finite time.
So first of all, of course, so the elliptic curves in the smart cards are really over finite fields. They're not over the rational numbers. So they're computing with finite number systems. But in terms of how rapid, and there might be special purpose algorithms that do these particular calculations very quickly. But again, I know nothing about engineering. So unfortunately, I have to plead the fifth. Yeah. I'm sorry. I'm sorry. I mean, to me, it's instantaneous because I just write 2x, right? So I don't. Yeah. Yeah.
You mentioned in the Escher Escher circle print that when he wrote to Coxeter, Coxeter just drew a circle and a line and sent that back to him.
Right.
Does that have anything to do with the fundamental sort of symmetric structure of the circle, or was it just some trick that Coxeter sort of thought?
I don't know how Coxeter thought about these things. I mean, I like to think about, there are two separate issues involved. What I explained to you is mathematically how there was this very elegant symmetry in the picture. What Escher really wanted to do, because Escher didn't know about non-Euclidean geometry, is he wanted a method using just the tools of Euclidean geometry, like straight edge and compass, to actually construct these things. So he did not want to have to compute hyperbolic reflections. So what Coxeter was trying to do is to explain how you could see this in a Euclidean way. But to me, it seems pretty cryptic, too. But there is, I should say, in the list of references, there is an article which actually does explain all of this. Yeah.
Elizabeth?
Yes.
So if you want to make a circular arc that uses the circle at right angles, you take the line that goes from the base perpendicular and the other line, the two of them from the 2 points where it was draw the circles. The 2 lines intersect at the Euclidean center of the circle.
And? Oh, I should say, that it's true that if I gave you 2 points in the boundary of the Poincare disk and you want to make the arc joining them, so there are certainly quick ways of doing that. The problem that Escher was facing was how to make very specific arcs, not just to make ones between arbitrary points. So you have this initial big hexagon, and you have to make very specific ones so the bird pattern continues. So the problem is a little bit different. Yeah.
Are there any further questions?
Yes.
I'd like to recommend the film Knock, which shows the hyperbolic three-dimensional space and explains things about regular subdivisions.
Oh, yeah. In fact, I should say that, yeah. Right. This hyperbolic geometry in the plane has an analog in any number of dimensions, and already even in 3 dimensions, it's quite different from usual 3-dimensional geometry. So yes, this movie Not is quite excellent.
I have a question.
Yeah.
If somehow you texture map that middle picture on a sphere.
Which middle picture, top or bottom?
The birds, the white.
Yes.
Yeah, the Escher picture.
Yes.
Will every bird be of the same size?
No. So hyperbolic geometry and spherical geometry are completely different. Okay. So this picture really reflects something about, as I said, this so-called hyperboloid, which I won't get into here, but the geometry of these surfaces is wildly different. And so if you try to put this on there in some way, it's just going to kind of completely screw it up. So the elegant symmetry is only seen on this hyperboloid, whatever that is.
So, but they'd have the same size hyperbolically, right?
Yes.
I'm not sure how to exactly frame my question, but I'll point out something. Hopefully you can see whether you can kind of frame it and answer it. It's something to do with the dimensions. Today we're talking about whatever here, a lot of things we're talking about 2 dimensions.
Yep.
The spiral thing, whatever. I mean, if some of those being put in a 3-dimension perspective,
yes.
I think it will be totally different thing.
Okay.
Not yet. And then my question actually really for you is, in our research now in the math circle.
Yes.
When would that kind of 3-dimensional to be a norm and real 3-dimensional thing versus just visually like put 3 dimension into 2 dimension? When would be a kind of normal way to really put everything really into 3D versus just on a 2-dimensional to do the discussion?
Okay, unfortunately, I didn't understand the second part. We can discuss that afterwards. Okay. But for the first part, let me just point out one thing, which is when we talk about reflections, okay, that reflection in the plane is not a kind of physical thing. I mean, when you look in a mirror, right, it's sort of fake what's on the other side. And in fact, it's not really a rigid motion of the plane because it screws up your notions of left and right, right? Every time you look in the mirror, somehow you raise your left hand and you get kind of disoriented as to what the person in the mirror, which hand they're raising their right hand. But on the other hand, if you bring in an extra dimension, right, then you can realize a reflection as a motion, right, as a rigid motion in higher dimensions. So even if you have a problem in 2D, if you bring in 3D, certain unphysical operations, in fact, become more physical. And the same thing when you do reflections through a mirror in 3 space, if you appropriately set it up in 4 dimensions, you can realize that again as a kind of rigid motion. So even in low-dimensional problems, it can be useful to sort of trick your mind into thinking in a higher dimensional way, but it depends on the situation. Yeah.
Anyone else? So could we all thank Brian Conrad for a wonderful... As you go out, I want to alert you to there's some pamphlets on the Bay Area Science Festival. As some of you may know, this is actually part of that festival. Please feel free to take one. There's still lots left to the festival.